going back to our equation, we have R total is equal to the following. Okay, so by the way, let's rename this equation. So say this equation here is our equation 1, and this equation here, RT for RT, is our equation 2. Okay, so referring now to our equation 2, so we have this RT. And last time we've computed the values of this individual resistance. So we can now substitute each values. So for our RA, we have this 5.21 plus 1 all over 1 over our RC is 7.8 times 10 to the negative 3, 7.8 plus our RB is just a 19.5 plus our RC is also this one, 7.8 plus this part here, 1 over our RD is 13.9 plus our RE is 6, right? 6 plus our RF is 31.2. So by the way, this is all equal to times 10 to the negative 3 K per watts, right? Okay. So all in all, our RT is equal to, what is our RT? 43.85 times 10 to the negative 3. Okay, let's check if my computation is correct. This part here is 5.21, so let me summarize this part. So this part here is equal to so we have this 3.25, of course, times 10 to the negative 3, and this part here is 4.19 times 10 to the negative 3 Kelvin per watts. Okay. So later on we can use these values also. So all in all, 5.21 plus this part here is 3.25 plus 4.19 plus 31.2 is equal to 43.85 times 10 to the negative 3 K per W. Okay, so let's go back to our figure. This part here, RA, is this part, this one, and this part here, the combination, the parallel combination of C, B, and C is this part, or equal to this part, 3.25. And the combination of D and E parallel is this part here, 4.19, and our F here is just this one. So all in all, we have this total 43.85 times 10 to the negative 3. Now, going back to our equation 1, wherein we need to determine the rate of heat transfer through the wall using this equation, equation 1. Delta T, we have our delta T, and our RT is equal to this part. We can now solve for Q using equation 1. So our equation 1 is this part here. The heat transfer through the wall is equal to the delta T and RT, wherein our delta T is from 0.1 to 0.5, this part here, our overall heat transfer through the wall from this point up to this point. So we have this Q. So our Q here is 300 minus 100, which is 200 degrees C. So we have 200 degrees C. And our RT is, where is our RT? Right there. So we have 43.85 times 10 to the negative 3 K per watt. Since this is delta T, we can easily cancel this out, by the way, and come out with the unit W. So this 200 divide this value is just equal to 4557.89 watts. So for letter A, our rate of heat transfer through the wall is just equal to 4,500 plus watts. Since we've already know the heat transfer through the wall, we can now compute we can now proceed to letter B, which is the temperature at the point where section B, D and E meet, which is the temperature at point 3. So let's now solve for temp at point 3. So let's call this as T3. Okay? So we can also, for letter B, this is for B. We can also use the equation delta T all over RT, but we will only now consider the sections where we can solve the temperature at point 3. Okay? So going back to this figure, using figure 1, we can now say that our delta T here refers to this point 3 and point 1. So say point 1 T1 minus T3. So this is delta T here is equal to T1 minus T3, which is equal to 300 minus our T3. So we'll now determine the value of our T3 here. Okay. And using this equation, say this is our equation 3. Using equation 3, our RT here now refers to this composition only, from point 1 to point 3. So these regions only, A, B, C, and C. So we will only consider the RT as the compositions of these resistances, So our RT here, so using this figure, so we have resistance of this A from 0.1. So these are RA, and 0.2 up to this 0.3. So this is 1, 2, and this is now our 0.3. This is our 1, 2, and 0.3. So because we need to determine this 0.3 here, the wall or the temperature between these materials. Okay, so by using this composition, we can now determine the RT, which is RA plus this part here. This is our RC, RB, and RC, which is, since this is a parallel, we have 1 all over 1 over RC plus 1 over RB plus 1 over RC. Okay, so using this and going back to our computations last time, so we've already take the value of our RA, which is 5.21 times 10 to the negative 3 plus this whole parallel combination here, which is equal to this part here is equal to this part, right? So this total resistance here is just 3.25 times 10 to the negative 3. So plus 3.25 times 10 to the negative 3. This is also times 10 to the negative 3. K per W. Okay. So our RT here is just equal to just equal to 8.45 times 10 to the negative 3 K per W. Okay. Since we've already know the value of our RT, we can now substitute it in our equation 3. And our Q is just also equal to this one, so 4,000. We can now solve for the temperature 3, since we have all the values except from this one. Okay. So using equation 3, let me use another paper. Okay. So using equation 3, which is equal to Q delta T over RT. So our Q is, since our heat transfer rate is equal to 4557.89 watts, then our delta T, which refers to this one, this part, T1, our T1 is 300 minus T3 all over our RT is this one, 8.45 times 10 to the negative 3 K per W degrees C. So using the algebra, the value of our T3 is now equal to 261 degrees C. So manipulating this equation to find the value of our T3, we can now get the value which is equal to 261 degrees C. Okay. So that is that is the temperature on this side, or at this point. So from 300, goes down to this temperature, which is 261 degrees C. Okay?